All right, welcome back to Calculus 2. I'm going to start recording the video here at home. I'll try it again at my office on Monday, and we'll see what works better. And once I get into a routine, we'll see about spicing things up with puppets or whatnot. All right, so let's get started in chapter 11. Chapter 11 is over sequences and series, so we'll start with sequences. A sequence is a function. We'll call this first one, so as an example, A sub n. We use subscript notation with sequences, but n is like your variable. It's like a function with your variable n here instead of x. So rather than function notation, we use this subscript notation. So when we have this formula here, this would be called the general term of a sequence. Need to figure out a better way of rigging up my whiteboard here. But if we start to list out terms of the sequence, a sub 1 would be the number you get by plugging in the subscript 1 in place of n here. So 1 over 1 squared, that's a square. Should be 1. A2 would be 1 over 2 squared, which is 1 over 4, and so on. A sub 3, 1 over 3 squared, which would be 1 over 9. Okay, so a sequence is a function whose domain is essentially the natural numbers or the positive integers or non-negative integers sometimes. Some notation you see with these. So if you write it like this, just did that one. Some notation you see sometimes looks like this. A sequence can be set up kind of like a set. It gives you a starting n value and then an ending n value, which for us will generally be infinity. These are infinite sequences for the most part. But this is the sequence as a set. And if you want to list out the first, so some of our beginning exercises are things like list the first 5 terms of this sequence. All that means is we are plugging in, starting with n equals 1. So a1 here, if this is an, this is a1 would be 4/3 to the power 1 minus 1. So 4/3 to the 0 power, which would be 1. A2 would be 4/3 to the 2 minus 1 power, which is 4/3 to the first, which would be 4 over 3, and so on. A3 would be 4/3 to the 3 minus 1, so 4/3 squared, which would be 16 over 9. And I asked for 5, so we have two more to go. A4, 4/3 to the 4 minus 1, so 4/3 cubed, 64 over 27. Then finally A5 would be 4/3 to the 5 minus 1, 4/3 to the 4th. I just realized I left my calculator elsewhere. 4 to the 4th power. So 3 to the 4th is 81. 4 to the 4th would be 16. So 4 times 64. I'll have to edit this out here. 240 plus 16 is 256. I knew that. Okay, so it goes on forever, but these are the first 5 terms of this particular sequence. All right. I have an idea. We have what are called alternating sequences. So this is just about terminology here. We'll frequently have these sequences where there'll be a -1 or just a negative number raised to a power of n. So -1 to the nth power times something else, say n plus 3, for example. So if we just list out a few of these, I won't do 5 again, but a1, -1 to the 1st power times 1 plus 3 is 4. That'll give me -4. A2, -1 squared times 2 plus 3. Now I'll have a +1 times 5, so +5, and so on. And so what happens is every time we increase n, the power on this -1 goes up by 1. So it'll alternate between minus sign and a positive sign. So this this one would be -6 a4 -1 to the 4th. 4 plus 3 will give +7. And so the alternating part of this terminology means the sign of our terms alternates between positive and negative. Okay, so these can appear in different forms, but a common form is to have some formula for your sequence, but then attached to that is a multiplier of -1 to the nth power, or -1 to the n plus 1 power, or n minus 1 power. And the difference is when it's just n, the odd terms of our sequence are the negatives. If it was n minus 1 here, then it'd be reversed. We have positive numbers for our odd terms and negative numbers for our even terms. Okay, so we'll see these things fairly often eventually. The other construction I should mention is factorials. So factorials, the symbol for factorial is an exclamation point. So what factorials mean, let me start with a larger one just to get us started. If you haven't seen these before, when you see a number factorial, so 5 factorial is how this is read, 5 exclamation point. What this means is you start with the number 5 and you work your way down until you get to 1 with multiplying by each number. So 5 times 4 times 3 times 2 times 1. And so that's a product. So I'll move this. That's 20 times 6 is 120. So 5 factorial equals 120. Once we understand the definition, though, it's kind of easier to work through these progressively. So first of all, 0 factorial is by convention equal to 1. Okay, the reason for that, I don't want to get too deep into the reason for that, but 0 factorial, this definition doesn't make sense. If I start with 0, I can't work my way down to 1. So 0 factorial should be, you might think of it as what we might call an empty product. An empty product should equal 1. Because if you start to multiply it by more things, you don't want it to be 0. You want it to gain those new factors. So 0 factorial is 1, because that means when you do 1 factorial, each factorial is going to build upon the previous one. So 1 factorial would just be 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, and here's what I've been trying to get at. This 2 times 1, that's the previous factorial. So this is 3 times 2 factorial. So 3 times 2 would be 6. 4 factorial would be 4 times 3 times 2 times 1, but that's just 4 times 3 factorial. So it's 4 times the previous answer. So 4 times 6 would be 24. 5 factorial. This way of thinking about it, 5 factorial would be 5 times 4 factorial. 5 times 24 would be 120. Okay, so if we keep going, these start to grow pretty fast. We'll do one more here. 6 factorial would be 6 times 5 factorial. So 6 times 120 would be 720. If we keep going, the numbers get larger and larger, faster and faster, so we'll stop there. The factorials will be a very important building block for some of our sequences down the line. Okay, so most graphing calculators, I don't have mine with me, but most graphing calculators, if you go into the menus, in like the math menu, I think on the TI calculators, the math menu, under PRB, I think, I'll you have to find it on your own calculator. I'll look for it later. They have factorial functions. So look for the exclamation point in the menus, and it should be there. All right. But maybe more importantly, we're not going to be calculating factorials so much. We want to be able to work with them, however. So let me look at some of those. All right, so we'll see things. I'll just call this an example of simplifying a factorial expression. So suppose we had n factorial divided by n plus 2 factorial, where n is a variable, so it doesn't have a specific number. But this expression, a lot of times we will see factorials occurring in pairs or in combinations, and we want to be able to simplify this to get a easier expression that doesn't require us to calculate these large factorials. So it turns out when we are dealing with this kind of situation, there is a significant amount of cancellation that occurs between the top and the bottom of this fraction. So I don't want to write it out this way, but if we thought of it by our initial definition for factorials, n factorial would be n times, so we start with n and we work our way down to 1. So n times n minus 1 times n minus 2, and so on, all the way down to 2 times 1. And so that n factorial would expand like that. N plus 2 factorial, if we did the same thing, would be n plus 2, and then we work our way down until we get to 1. The next number would be n plus 1. The next number after that, we just keep subtracting 1, so the next one would be n. After that, we'd have n minus 1, and so on until we get down to 2 times 1. And the point is, the top is everything from n downward. The bottom has n and everything below it. It just has a couple extra factors before it. But there's going to be cancellation. N cancels with this n minus 1 cancels with this n minus 1, and so on. So this entire numerator cancels with most of the denominator, and we're left with nothing on top. So if we cancel everything, we have a 1 left over, of course. On the bottom, we have n plus 2 times n plus 1. And that's relatively simple. It's just a number divided by a simple polynomial now. All right. So the faster way to thinking of this is when there are two factorials and you're dividing, you think about which one is bigger. So n plus 2 is bigger than n. And then you think, how many extra factors will this denominator have that this numerator didn't? So it has everything above n, so and below n plus 2. So it has n plus 1 and n plus 2. That's what's left over after canceling. So let's look at another example that's similar. All right, so same idea here. N plus 3 factorial divided by n minus 1 factorial. So just to do a similar problem, but in a faster way here. So if we're trying to cancel common factors here, they're both factorials. The top one is bigger. So what's going to happen is this top will have everything that the bottom has. So the denominator is completely going to disappear, and we're going to be left with only those numbers which are bigger than n minus 1 and less than or equal to n plus 3. So we just start writing out this top factorial here until we and stop before we get to n minus 1. So we'd have n plus 3 times n plus 2 times n plus 1 times n. If I kept going, then I'd hit n minus 1, but that's all going to cancel with this denominator. So these are the factors that are actually remain after we do our cancellation. All right. So that's still just talking about some basic types of sequences. Now let's get into the actual calculus of sequences. So we're going to talk about limits of sequences. All right. Let me do the definition first. So we're going to talk about the limit of a sequence an. The only so as with functions, the limit of a function, limit of f of x, we can ask what is the function approaching as x approaches whatever number we want, or whatever number makes sense. For a sequence, it doesn't make sense to ask what is the limit of an as n approaches 3, because you can't get arbitrarily close to 3. The only values that n can take are whole numbers, so you can't get very, very close to 3 without already being 3. So instead, the only thing that it makes sense to ask is, what is an approaching as n approaches infinity? It's an infinity there. Okay, so the only kind of limit that we worry about with sequences is the limit as n approaches infinity. So if this equals a number L, this means let me start with the formal definition, and then we'll do it more informally. So this equation here, saying the limit of a sequence equals L, that means for every number epsilon greater than 0, there is a there is an integer capital N such that for all little n bigger than or equal to capital N, we want to say the terms of the sequence will be very close to L. So they'll be within epsilon of L. So that the way we said it is the absolute value of AN minus L is less than epsilon. Okay, so this is the fancy way of saying this, but informally and more understandably, it's the same kind of definition we had for limits of functions as x approaches infinity. So let's draw a picture here. If we wanted to talk about the graph of a sequence, we kind of have our n-axis here, and then our y-axis would be like the a-axis or a sub n-axis, and the only inputs that make sense are the whole numbers. Maybe 0, not always, but maybe 0. So the graph will only have points over each of these whole number inputs. So if I graph it, I get this sequence of dots. And as we go off to infinity, as n goes off to infinity, which is out in that direction, maybe these dots start to level off. They might not, or they might. But if they level off towards some number, so maybe this is L here. Actually, let me redraw this. I don't want it to level off to 0 necessarily. I'll make it an increasing sequence just to make it a little bit easier to follow. And I've got some other colors here. So maybe L, hope that's visible. Maybe L is a number up here. And so we can think about L as a horizontal asymptote. If the limit of the sequence is L, all that means is that if we go sufficiently off in that direction, our dots will be closer and closer to the horizontal asymptote. So the epsilon stuff, that's just a formal way of describing it. What epsilon is it's telling you how close you want to be to the limit, to the horizontal asymptote. So once you pick an epsilon value, then that means I can think of a neighborhood around this asymptote. And no matter how small I make it, no matter how thin I make this strip, if I go far enough out in that direction, all my dots of my sequence will be within that strip. And after a point, we never leave the strip. So if you pick a smaller strip, that just means I have to go farther out in that direction. But essentially, the good news is, essentially, for most of the sequences we deal with, the tools we use for computing these limits are very similar to a lot of the tools we use for limits for functions as x approaches infinity. All right, so let's talk more about that and get into some examples. Okay. Okay, so let me start with this fact here. This kind of goes back to what I just said. If we have a function f of x, and the limit of this function as x approaches infinity equals some number, and we have a sequence a sub n, which is basically the same as the function. So a sub n is equal to f of n, then the limit of the sequence as n approaches infinity is the same as the limit of the function as x approaches infinity. So this is kind of abstract what I'm saying here, but the idea is this. A function has some domain. In general, you can plug in any real number within the domain into the function. So this function is defined for basically any x, any real number x. The sequence is only defined for whole number inputs. So what we're saying is, if the function agrees with the sequence on those integer inputs, on those whole number inputs, then we can look at the limit of the function, compute it. It'll be the same as the limit for the sequence. Okay, so let's do this with a concrete example now. All right, so for example, let's do a simple one first. So this is the first example we did here. So 1 over n squared is what that's supposed to say. Let me rewrite it. Limit of 1 over n squared as n goes to infinity. Just to remind you of the intuition with some of these infinite limits. As n grows to infinity, the denominator here is growing larger and larger. The numerator is just a number, so 1 divided by a very large number is going to be a very small number. So as this denominator grows to infinity, informally we think about what is 1 divided by infinity. That's 0. Okay, so limit of this sequence is 0. The intuition that we use here is the same intuition we used back in Calculus 1 when you're doing the limit as x approaches infinity for something like this. However, suppose we had one like this. The limit as n approaches infinity of e to the n over n if you try to think about plugging in infinity for n here, you get e to the infinity, that's infinity, divided by infinity, that's also infinity. So infinity divided by infinity, that's one of our indeterminate forms back from the L'Hopital rule chapter in Calculus 1. So this would be, if these were x's instead of n's, this would be a L'Hopital's rule problem. And in some sense it still is, but only because here I'm using n to represent whole number inputs. But if I replace n with x, I get the function e to the x divided by x. That still makes sense for real number inputs x. Okay, so it doesn't look like I did anything here. I just changed the variable name from n to x. But the point is, this function makes sense even for non-whole number inputs. So that's what I'm indicating when I change n to x, is now it's a function of real numbers. And with functions of real numbers, I can use L'Hopital's rule in these indeterminate form situations. So at this point, in this situation, I'd say I'd use L'Hopital's rule, indicate with a LH there. And with L'Hopital's rule, we take the derivative of the top and the bottom. That'll give me e to the x over 1. And now we try to plug in infinity again. This is e to the infinity is infinity, divided by 1. That's infinity. Right? So the point of this, the fact that I erased from the previous board I had here, means if I'm trying to take the limit of a sequence, if it makes sense to replace n with x and it still makes sense as a function, then I can use whatever tricks that we used in Calculus 1 to find these limits, including L'Hopital's rule where it's applicable. That's in indeterminate quotient situations. Let's review another frequently appearing type. So we frequently have these rational function sequences. So what I mean by that is limits of an expression where it's a quotient, where the top is a polynomial and the bottom is a polynomial in the variable n. So something like 5n squared plus 3 divided by 4n squared minus n plus 1. Okay, so if I try to plug in infinity for n, I'm going to get some infinite expression divided by some infinite expression. The good news is, in these rational situations where it's just involves polynomials or powers of n raised to different powers, I mean, those functions make sense whether n is a natural number or a integer, or a real number. So I can replace n by x and use L'Hopital's rule if I wanted to. But just to remind you, there's a quick rule. Another way we could have done this, besides L'Hopital's rule, is if we manipulate this fraction by dividing every single term by the largest power of n on the top and the bottom. So I'm just doing this. I'm dividing by n squared on the top, and I'm dividing by n squared on the bottom. And then doing that, distributing these 1 over n squareds. I'm just dividing every single term by n squared. What that leaves me with is 5, because the n squared will cancel with this n squared, plus 3 over n squared divided by 4 minus n over n squared would be minus 1 over n, and plus 1 times 1 over n squared would be 1 over n squared. And then all of our basic limit rules apply for sequences. So if I want to know what happens to this now, each of these little fractions, 3 over n squared as n grows, that's 3 over infinity. That's going to go to 0. Let me get another color here. 3 over n squared, that approaches 0. 1 over n, that approaches 0. 1 over n squared, that approaches 0. All that's left is the 5 and the 4. So our answer is 5 over 4. So in practice, the quick rule, since we see this stuff a lot in certain situations, the quick rule is, you might remember this from college algebra also, but definitely from someplace in the past, if the top and the bottom have the same degree, so same power of n, the limit as n goes to infinity is just the ratio of their leading coefficients, so 5 divided by 4. If the bottom has the bigger power, so if it was just 5n over 4n squared, then when I do this, the entire top will go to 0 and the answer would be 0. If the bottom had smaller power, so I didn't have the n squared here, then when I do this trick, I'd be left with a number divided by 0, which would be infinite. My answer would be either positive or negative infinity depending on the other signs. Okay. Another category of examples we want to talk about specifically is geometric sequences. So let's do a quick example with a specific sequence. So a geometric sequence is like an exponential function. So 3/4 to the n. Well, if you just think about what happens as n grows, each time you increase n, you're multiplying by 3/4 again. So the more you multiply by 3/4, the more it shrinks. So 3/4 times 3/4 will be 9/16 times 3 again. The top's growing slower than the bottom. So if it's a small number, like a small fraction like this, the limit's 0. On the other hand, if it's a large fraction, well, let's just do 2. Don't have to use a fraction. The limit of 2 to the n, the more times I multiply by 2, the more times your terms double. So each time you increase n, your sequence term is doubling. So this is going to grow to infinity as n grows to infinity. Okay. Let me actually write another one out specifically. So one thing that so far we've these two sequences would also make sense if it was x, if we were dealing with real number inputs rather than whole number inputs. But an example or a class of examples that wouldn't make sense with real number inputs would be things like this: -1/2 to the n. If we want this, I'll come back and answer it, but let's write out the first few terms. Let's not get ahead of ourselves. So I'm just listing out some terms here. -1/2 to the first power is -1/2. -1/2 squared. Since it's squared is an even power, the minus signs will cancel and give us positive. This will give us 1/4. -1/2 cubed. Since it's an odd power on the minus sign, it'll give us a negative output. 1/2 cubed would be 1/8. If we keep going, -1/2 to the fourth, even power will give us a positive output, and we'll have 1/16, and so on. And this is an example, like we talked about, this is an example of an alternating sequence. We're alternating between negatives and positives. But if you ignore the minus signs, the numbers themselves are shrinking. So the numbers themselves are approaching 0. I'll draw a picture here in a second. I don't have enough space here. Our limit will be 0, but let me draw you a picture of what this looks like. So when n was 1, we had -1/2. That'd be down here someplace. When n was 2, we had +1/4, so that'd be up here someplace. The y value would be half of this distance. And so what we're getting are dots that are alternating signs. They're alternating back and forth between bottom and top, but their sizes are still shrinking. Should use a different color, I guess. They're ping-pong up and down, but it's narrowing in on the axis there. So it's narrowing in on a y value of 0. So the limit is still 0. Okay, now I'll say more about this in a minute, but how much time? Yeah, say more about this in a minute, but this specific sequence, when you have this minus sign raised to the nth power, you can't raise negative numbers to certain exponents. Like you can't raise -1 to the 1/2 power and still get a real answer. We get imaginary answers in that situation. So this kind of sequence does not make sense if I put an x there. You can't turn this into a function. So if this cropped up in a fraction and we were getting 0 divided by 0 where the numerator was this expression, L'Hopital's rule wouldn't work. It wouldn't make sense in that context without some additional manipulation. Okay. So I'll come back to that idea in a little bit. Yeah, we may cut the video in a minute and then start a new one. I wanted to say one more thing. The general rule for geometric sequences. Just erase this, so geometric sequence in general has this form: r to the n for some number r. I suppose they can also have a number in front of it. So like this, a times r to the n. So the answer to this, the limit of this geometric sequence, like we saw with our examples from before, it depends on the base r. Depends on how big this number r is. So the first situation was if r was a small number, if r was 3/4 or -1/2, our geometric sequence approached 0. So we get a 0 for our answer if the absolute value of r is less than 1. I guess I should be careful here. Actually, no. So what else can happen? If r was exactly 1, 1 to the n is always 1, so I just get a. So if r equals 1, I'd get a as my answer. I guess I want to assume here that a is not 0, otherwise some of this will seem silly. Then the third possibility is, other than these two situations, let's say does not exist. I don't want to say infinity because it might not go to infinity. It might alternate between very, very positive and very, very negative, or it might do other things. But the limit does not exist if the absolute value of r is greater than 1, or if r equals -1 exactly. Okay, if r equals -1, then this is just going to ping pong back and forth between positive a and negative a. If r is a big number, so if r is a big positive number, then this is going to, and a is positive, this is going to grow to infinity. If r is a very big negative number, then it's going to be ping ponging back and forth between very big and very negative. Okay. So we have a general rule for geometric sequences. One other bit of terminology I neglected to mention. So does not exist here. Let me make sure to include this. Should have said this way back at the definition of limit for sequences. But I may be getting my classes confused here. So a sequence AN, a sequence AN converges if the limit of AN is finite, so it exists and is finite. It diverges if the limit is infinite or otherwise doesn't exist. So it does not exist. Or that includes plus or minus infinity. So if it's infinite, that technically does not exist, but it's a special kind of not existing. So this is similar to back when we talked about improper integrals. Convergent if the thing had a finite answer, divergent if it didn't. All right. So there's still more to say about section 11.1. To keep things manageable, let me stop this video early, and then I'll start a new video with the rest of section 11.1. So like I said, I'm recording this a little bit early. I still haven't. It's still Friday before we come back before spring break is over. So I don't have the final answers about some of the questions about how we're going to proceed with exams going forward. But like I explained in my initial email, my plan for quizzes is I'll treat them more or less like I did when we were meeting face to face, in that I will assign you problems from the textbook for each section to have you look at, and so you should practice those to get a feel for the material, and then at some point I will post basically a quiz on Blackboard with the statistics tracking turned on so I can see who accesses it. I'll treat the quizzes as a participation grade, which just means I will look to see who has downloaded it, and I will trust that you attempted it on your own, but then I will come back and create a shorter video going over each quiz, so you can compare your answers to my answers. So I'll let you know as soon as I can more information about exams. We still have quite a bit of several weeks before I have to worry about that. But sometime next week I'll try to get the next quiz posted so we can get that part of our routine settled. So if you have any questions about the material from the lectures, the videos, you can either email them to me, or you can, I'm intending to post this on YouTube. You can also post comments there and discuss it in the comments if you want. I can answer comments there, I think. But another option is, if there are topics that you need to see more examples of, try to ask the question in email or in comments, and if necessary, I can come back and make extra videos where I respond to student questions. Okay, so I will cut the video here and make another video for the rest of 11.1, and in that video I'll have a problem list for that section. Alright, let me stop this and start the